All right, guys, we're going to do some more practice for the exam on Monday. I've decided to eliminate section 9.9. Don't feel like I need to add any more stuff for you guys to do, so we're just going to do some more practice problems. This is the auxiliary lecture that goes along with Monday, and then we'll do another practice session tomorrow, and then Friday I'll get into the new material. So that's a lot of practice. I hope that it benefits you guys. Okay, so I'm going to pick up with power series. So we're looking now at this example, the series of, I got the right one? I want to start here, yeah. So we're starting at n equals 1 to infinity, -1 to the n minus 1, 3x minus 1 to the n, all over n squared. And as before, our goal is to find the radius of convergence and the interval of convergence. These are the two things that we want to find. To find the radius and the interval of convergence, we start by applying the ratio test to the series. So we're going to be looking at the limit as n goes to infinity of 3x minus 1 to the n plus 1 all over n plus 1 squared divided by 3x minus 1 to the n over n squared. And then we're looking at the absolute values of these things. And this simplifies. We'll end up with n squared over n plus 1 squared times the absolute value of 3x minus 1. Okay? And we're still taking a limit here. Then goes to infinity. So in terms of n, we have a rational polynomial that whose leading power in the top and the bottom are the same degree. So they're going to converge to the ratio of the leading coefficients, which is just going to be 1. So it's going to converge down to 3x minus 1, absolute value. And we need, in order for this to be convergent, we need that this is less than 1, right? That must be the case. Okay. So sometimes you get the radius of convergence immediately when you apply this inequality. Sometimes you got to massage it a little bit. There's a couple different things we need to do here. Well, there's one main thing we need to do here, which is get this absolute value into the right form. So it should be x minus the center of the power series. And right now it's not in that form. So what I'm going to do is I'm going to factor out the 3 from the absolute value. And then divide that 3 over. So we end up with this inequality, and this tells us two things. One, that our power series is centered at 1/3, and the other is that our radius of convergence is 1/3, right? So we get that r is equal to 1/3. That's the first thing that we needed to find, and we have found it. Now we need to find the interval of convergence. So we're going to break up this inequality and get it down to something just in terms of x. So I can break it up like this. X minus 1/3 should be less than 1/3, which and x minus 1/3 should be greater than -1/3. So if we get x by itself in the compound inequality, we'll get x is between 2/3 and 0 by adding that 1/3 over. So this is the radius of absolute convergence. We definitely have absolute convergence in that open interval. We still need to check the endpoints, however. So I'm going to transfer up here. I got more room. So let's check the endpoints. What happens at x equals 0? If I plug in x equals 0, then what does the series turn into? I just get a -1 to the n minus 1, and then a -1 to the n, and that's all over n squared. I've got to do something to simplify this just so I can see what's going on. So these are like bases, so I can combine them together. And I get -1 to the 2n minus 1 all over n squared. And here's the trick. 2n minus 1, I look at that as a power, and for every n that I plug into it, it spits out an odd number. If I'm raising -1 to an odd number, I'm always going to get -1. So this will simplify to just negative the series from 1 over n squared, because that -1 just turns into -1, or factor it out. Or I can keep it in. Actually, we can keep it in. That's fine. And that way I can say, if I looked at the absolute value of the sequence and looked at the series of it, that this is definitely absolutely convergent, right? And that's by the p-series test. So it's an absolutely convergent p-series. All right, so then I need to check 2/3. That's one endpoint checked. Let's check x equals 2/3. And when we do that, what does our series turn into? It turns into -1 to the n minus 1 and 1 to the n when we plug in 2/3. And so that's just going to equal -1 to the n minus 1 over n squared. And so this is an alternating p-series, and our p-value is greater than 1. So we've got absolute convergence. And that's by definition, really. By definition and p-series test put together. So that's the whole breakdown, right? We need to find the radius of convergence and the interval of convergence. And so this puts it all together. We've got absolute convergence at both endpoints. So when I put down the IOC, we say it goes from 0 to 2/3, both inclusive. So we've got absolute convergence across that whole closed interval. Okay. I'm going to pause to see if I can find a better marker. All right, I'm just going to have to switch to blue. My black can't find any black markers, fortunately. All right, let's do some more power series. Right. So maybe some quick ones. We're looking at the series. Oops, sorry, hideous. Okay, we're looking at the series x to the n over n to the n. And that's starting at 1, going to infinity. Right, so same deal as before. Look at the ratio test. And we're going to get x to the n plus 1 over n to the n plus, or sorry, n plus 1 over n plus 1 to the n plus 1, sorry, all over x to the n over n to the n. looking at the absolute value of that. So simplify it. And we get n to the n over n to plus 1 to the n plus 1 over times x. And, get us to make a pretty hand-wavy argument here and say the top is growing at the same rate as the bottom, right? They're both to the ends, basically. So I know that this is going to converge to 1. If I want to show it, I would have to go through L'Hopital's rule and all of that. At least I think that would be the way I want to show that that sequence goes to 1. Or maybe I could just do a comparison, thinking about that. How would we show that? Well, we can do L'Hopital's rule. Let's just take a look. So we're just looking at this piece right here. So that's going to be, we're going to translate it into a continuous variable, x to the x over x plus 1 to the x plus 1. Oh, I think my headphones are dying. Going naked. All right. And we did the whole thing that we usually do with these guys, which is say that's L, then we did the natural log trick. And in order to do that trick, I can do it. So we can take the natural log of the whole thing. And we'll get natural log of x to the x over x plus 1, x plus 1. And of course, that's equal to the natural log of our limit. And then we're going to use log rules on this. So we can write that as a difference of logs. Let's squeeze it in over here just to save room. The limit. And I'll have the natural log of x to the x minus the natural log of x plus 1 to x plus 1. The limit of that whole thing. Now we can use the log property and bring down the powers. And get x times the natural log of x minus x plus 1 times the natural log of x plus 1. And now what will we do? We will break it up and gather like terms. So I have an x natural log of x minus x natural log of x plus 1, and then we'll have a minus natural log of x plus 1. So let's see if we can do some algebraic maneuvers here. Pull an x out. So still got this guy. And then I can write this as a quotient. Actually, I'm just doing a lot of extra work for something I could have done pretty immediately. So now the best to show this. Not a bad thing for you guys to see me struggle for a second. I think I'm realizing that it's making extra work here. Could have been more direct. And just broken this up immediately down the bottom. And what do we get? We get natural log of x to the x over x plus 1 to the x times x plus 1. And if I plug infinity into that, obviously I'm getting infinity over infinity. So, so we can use L'Hopital's rule there. I really don't want to, because it's going to be ugly derivatives to take. So in this very slim case, because I just don't want to do the work, to be quite honest, I just know that the limit is going to be 1 by the same argument that we made before. I mean, we can see it here too, because we can see that this piece here is going to grow faster than the numerator. And so I'm going to get the natural log of, okay, let me just stop talking. Failing at this. Okay, I needed a second to stop and think about it, but this is one where we can be tricky. So how do I make the argument here? I'm going to do this one a little bit differently. And this is how I'm going to do it. I'm going to say, hey, I can rewrite this series in this way, x over n to the n power. And so this is a geometric series with a ratio of x over n. So we know that this is absolutely convergent if and only if its ratio, the absolute value of its ratio, is strictly less than 1. So that's all I need to do. I didn't even need to use a ratio test with this one. I had to take a step back and think, oh, there's a much simpler way to see this. And so what does this say? This says that the absolute value of x, that this must be true, but then I'm going to look at this in terms of the limit, because I need it to always be true. And if I do that, this clearly goes to 0. Right? This must hold for all n. Therefore, if I look at the limit as n goes to infinity, it must be true, and indeed it is true, because the whole thing goes to 0. So it's completely independent of the choice in x, in other words. So what this implies is that our radius of convergence is infinity. It's convergent everywhere for the largest a radius of an infinite radius, and the interval of convergence is just all real numbers. That's what's given. So a little bit tricky, right? But it's a way of making an argument. So this I see this as a geometric series whose ratio is x over n, so I know its absolute value must be less than 1. And I could say this must be true for all n. I want that to be true for all n, so in order for it to converge. In other words, we should be able to look at the limit, and it should be true, and the limit gives us 0, so that satisfies the constraint. Therefore, we have convergence, and indeed it doesn't depend on x at all, right? So infinite radius. That's a neat little problem. It gave me a little
sometimes going the direct route isn't the best. It's a little bit more complicated. We have to stand back and look at it a different way. Okay. Enough with that problem. Let's look at another one. Series n plus 1 x to the 2n minus 1 all over 3n, and starting at 1 and going to 0. Yeah, that's fine. Or I mean, it can start at 0. It doesn't matter. So let's do it. ROC, IOC. This one we do approach directly. This doesn't look like any series that we've seen before. So we do the whole ratio test thing. And what do we get? We get n plus 2 for x to the 2 n plus 1 minus 1 over 3 to the n plus 1 divided by n plus 1 x to n minus 1 all over 3n. Look at the absolute value of that. And what do we get? This reduces down to the limit and goes to infinity of n plus 2 over n plus 1. We'll have a 3n plus 1 over or under a 3n, so we'll end up with a factor of 3 in the bottom. And then we'll have this guy up here, that becomes 2n plus 2 minus 1, so 2n plus 1. So these two things differ by degree 2, so we just get x squared coming out of that, which is always positive, so the absolute values go away. And if we look at the limit here, we've got a rational polynomial, powers are the same, so that will converge to x squared over 3, and we know that this has to be strictly less than 1 in order to get convergence. So we could also look at the, this would imply, we move that 3 over, the x squared has to be less than 3, which is equivalent to absolute value of x being less than the square root of 3. Because when you take that square root of the square, you get absolute value, remember? So this tells us that our radius of convergence is square root of 3. Doesn't need to be a rational number, it could be irrational. And it gives us that what our IOC could be is something like this, but we'll need to test the endpoints. So take away the absolute value, break it into a compound inequality, and now let's look at the endpoints. So what happens when x equals the positive square root of 3? It's one of the endpoints. What does our series look like? Series will look like, I think the easiest way to see this is to write root 3 is 3 to the 1/2, 2n minus 1 over 3n, and do some algebra. Get n plus 1, and we'll have 3 to the n minus 1/2 all over 3 to the n. And then I can break off that negative 1/2. And when I do that, I'll just have a 3n left there. And so those will cancel. And that just gives us the series of n plus 1 over the square root of 3. And we know that this thing is divergent because the sequence doesn't go to 0. So this is definitely divergent. And we can say it's divergent by the very important theorem. All right, I think we can still see down here, hopefully. Let's test x at negative root 3. Do the same sort of thing. We'll try to skip a few steps here. This will be negative 3 to the 1/2 power 2n minus 1 over 3n. And now we'll distribute that power to the negative 1 here and the 3 to the 1/2 power and get n plus 1 negative 1 to the 2n minus 1 times 3n times 3 to the negative 1/2 all over 3n. Still visible, I think it is. And yet again, we get cancellation. This guy right here, we have a negative 1 to the 2n minus 1. 2n minus 1 is always an odd number, so that is always just negative 1. So we can pull the negative 1 out, and what do we get? We get the sum of n plus 1 over root 3. So we just got the negative addition, which is still divergent by the same logic as the previous one. So that tells us that our IOC is just that open interval from negative root 3 to positive root 3. So a fair amount of work on these problems, doing all this analysis, and we're going to be careful, right? So this one was centered at 0, as we can see, had a radius of root 3 and an IOC of an open interval between negative root 3 and positive root 3. All right. So I'm going to keep this session a little shortish. I'm going to close out with a Maclaurin series, a couple Maclaurin series. Right, so now we want to find the Maclaurin series generated by the function 1 over 1 minus 2x. Right. So how I'm going to do this is I'm just going to take the derivatives, take a few derivatives first, and then we'll figure out what the coefficients are. So remember, I made this mistake before. The general coefficient for a Maclaurin series is given by this expression, this equation. So I'm going to need a number of derivatives of f so that I can figure out the pattern. In this case, this is our f. So we'll take a few derivatives first. What's the derivative of f? We're going to look at that as a 1 minus 2x to the negative 1 power. So when I take its derivative, I'll get negative 1 over 1 minus 2x squared. And then I'm going to multiply that by negative 2, because that's the derivative of the inside function. So what does that simplify to? That's just 2 over 1 minus 2x squared. Let's take another derivative. I do another derivative. This time I'm going to get negative 1 over, sorry, not negative 1, I'm going to get negative 3 getting bad back there. So we want to look at this as, here, do this. What is f prime? F prime is 2 times 1 minus 2x to the negative 2 power. we want to take the derivative of that to get the second derivative. So what we're going to get? We're going to get negative. There's already a 2 there. We'll get another 2, a negative 2. This will now be to the negative third power. And then we will get another negative 2 coming out from the derivative of the interior. So a lot of 2's here. We've got 3 2's. But one of them is coming from the derivative of the interior, and one of them came from the power. So we might want to keep them separated, just to make sure we have the pattern. So we'll have obviously a positive, and I'm going to have a 2 times 2 squared. I want to do it 2 times 2 squared over 1 minus 2x to the third power. So I got 1, 2 from the interior, and then I got 2 more 2's on this iteration. 1 was from the interior and 1 was from the power. So that's why I'm keeping 1 separate. Okay. So maybe 1 more derivative. Third derivative. We're going to get, we have the 2 and the 2 squared already. We're going to get a negative 3 from the power, then 1 minus 2x in the bottom to the fourth power, and we'll get another negative 2 coming out from the interior of the function. So what does this simplify to? Again, we get something positive. Now we've got a 2 and a 3, and then 3 2's. So 2, 3, 3 2's all over 1 minus 2x to the fourth. All right, I think 3 derivatives hopefully should get us there. So if we plug in 0 for each of these, then the first one I'll get 2. The next one I'll get 2 times 2 squared. The next one I'll get 2 times 3 times 2 cubed. So what does this look like? This is when I get to this one, I've got 3 factorial times 2 to the 3. So in general, the nth derivative evaluated at 0 will be n factorial times 2 to the n. Okay. Right. So now what? Now we find the general coefficient, a sub n, and that will be n factorial 2 to the n all over n factorial. And so what do we get? We just get 2 to the n. So now we can write down the general Maclaurin series for this thing. And see down there. Yeah. So what is our general Maclaurin series? It's 2 to the n times x to the n. It's going from 0 to infinity. And so we know that this is equivalent to 1 over 1 minus 2x. Should be right. There's another way we can see this result, and perhaps another way we can shortcut this whole process. So Let's see if we get the right result. Maybe I fudged the pattern. Let's see. So another way to solve this problem is to realize that this function is the limit of a geometric series. How do I see that? So in general, the limit of a geometric series is this, right? So if I'm comparing these two things, then that implies that a equals 1 and r equals 2x. So if I were to write down the geometric series that satisfies that, that would be 2x to the n, starting at 0, which is indeed the same as 2 to the n times x, which is what we wrote down here. So another way to see the same problem. If you notice this and you can make that argument, then A plus. All right, that's a killer way to solve this problem. All right, rather than having to do all those derivatives, if you see, hey, that looks like the geometric series thing, I can use that to write down the series quickly. Now, it does need to be a Maclaurin series, so it needs to be centered at 0, as this one is. So if it weren't, if you had some other center here, you might have to do some fudging, but maybe keep an eye out for that one. I kind of like how slick that is. Okay, so how about one more? And this one's another good one, very much of this ilk. So same deal, right? But now we want to find the Maclaurin series. Generated by f of x equals e to the negative x squared. Okay, so let's find derivatives. This one's going to get ugly real quick as we start to take these derivatives. So take the first derivative, and we get e to the negative x squared times negative 2x. So that's negative 2x e to the negative x squared. Take the next derivative. And we're going to have to use a product rule here. So we'll say derivative of the first function is negative 2 times the second function plus the first function times the derivative of the second function, which is the same derivative that we found. I mean, this is the derivative of e to the negative x squared, right? So I can just put that right back in there. And what is that going to give us? It's negative 2 e to the negative x squared minus plus, because I have two negatives, 2 squared times x squared e to the negative x squared. Yikes. Or yeah, let's put 4 there, just why not? Yikes, right? And what can we do? We can factor that. So we can factor out a 2 and factor out a 2, and we'll have 2x squared plus 1 minus 1, sorry, e to the negative x squared. Okay, so already maybe we can find the pattern quickly because these derivatives are getting ugly. So if we plug in 0, we get 0 for the first one. So f prime of 0 is 0. F double prime of 0 is 2. Yeah. Good. And then what? So then we'd have to take another derivative. And what do you want to bet that when we find that and we plug it into 0, we're going to get 0. How might we see that? Well, we have to take the derivatives. So one of the things that I'm going to make a point about here is, I'm already exhausted, right? And there's more derivatives to take. The derivatives are ugly. I don't want to keep going. You know, I'm lazy, right? So I'm making a point here. We could go this route and get the answer, but it's going to be a lot of work. But there is a faster approach. And it's very much like what we did on the last problem. So we're looking for the Maclaurin series of e to the negative x squared. Well, we know what the Maclaurin series is for e to the x. That is this guy. So guess what? Just like what we did on the geometric series, if I want to know what this power series for e to the negative x squared is, I just replace the x with negative x squared. And if I do that, then I can simplify this, and I'm going to get negative 1 to the n, so I'm getting something that's alternating, x to the 2n over n factorial. So that's one of the reasons why we have these, we only get even powers of x. So we're going to get zeros every other time, and then it's also going to be alternating. But regardless, we don't have to go through all that work because we can just jump right to it. So bear that in mind. We've already derived some of these canonical series, right? We've derived the series for sine. We've derived the series for cosine. So if I ask you what's the series of sine to the x squared, you can use the same trick. If I ask you what the series of cosine to the 2x is, you can use the same trick. So knowing knowing all the canonical series can be really useful and speed things up. And I'm not discouraging you from doing that. Sometimes memorization is the best way. Memorize the common series for the big transcendental functions. Maybe you want to derive the one for the natural log of x and have that memorized. Maybe something like that would come up. And you can use that on the test. All right? Because I'm all for you guys. If you use smart shortcuts, I'm into it, right? I like when you guys are clever. It's when you try to do stuff that doesn't make sense that I don't like. So that I think I'm going to wrap up this problem session with that Maclaurin series. I think I'm going to be in class tomorrow. I'm going to drive home tonight, so we'll have an in-person class and do some more practice. All right? Okay.